Hey everyone, welcome back. Let's talk about another medium problem on Leetcode today, Decode Ways, Leetcode 91. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an intercepted secret message encoded as a string of numbers. This message is decoded via the following mapping. So 1 maps to A, 2 maps to B, 3 maps to C, and so on, all the way up till 26 mapping to Z. However, while decoding the message, we realize that there are many different ways we can decode the message because some codes are contained in other codes. For example, 25 can be treated as 2 and 5, leading to B and E, or it can be treated as 25 itself, leading to Y. Then our task at hand is, given a string S containing only digits, we have to return the number of ways to decode it. If the entire string cannot be decoded in any valid way, we should return 0. The test cases are generated such that answer fits in a 32-bit integer. Then in example 1, for the given numeral string 12, our output is 2 because 12 can be treated as 1 and 2, which will result in the string AB, or 12 itself, which will result in L. Hence, total number of ways in this case will be 2. Similarly, in example 2, the given string can be treated as 2, 2, 6, which will result in BBF, or 2 and 26, which will result in B and Z, or 22 and 6, which will result in V and F. Hence, total number of ways in this case will be 3. And note that digits starting with 0 are invalid. For example, here when decoding the string 11106, at any point, if we have to decode the substring 06, that will result in invalid code because in the mapping, none of the digits is starting with 0. However, decoding the substring like 10 is okay. So when working on the solution, we have to be mindful of that. Now in terms of solution, one of the naive approach for solving this problem will be to try all possible ways of grouping the digits in the string and check if the grouping forms the valid mappings to letters. This involves recursively exploring different paths for splitting the string while validating each possible grouping. For example, for this given string, we initiate the decoding process starting at index 0, and here we have two possibilities. Decode the single digit to SB and move to index 1. Note that if this character was 0, decoding will end here itself, as digits starting with 0 are invalid for mapping. However, if 0 was here and the string was 206, then we can still proceed decoding 2-digit substring, which is 20 in this case, as 20 is a valid encoding. Now, continuing with our example, another way to decode the string at index 0 will be to use 2-digit mapping, which will result in digits 22 and is a valid mapping because it is in the range 1 and 26 and can be decoded to V. And after that, we move to index 2. However, if this string was 322, then we will get digits as 32, which is not in the range 1 and 26. Hence, it is not a valid mapping. Now, at index 1, again, we can either decode one digit, which is digit 2 with value equal to B, and move to index 2, or we decode 2 digits, which will result in 26. And as 26 is in the valid range of mapping, which is 1 to 26, this is also a valid path. And this time we are also at the end of the string, which means the string was decoded successfully. So we will return 1 from this path, denoting one valid decoding. However, if the string was 2 to 7, then we would have gotten 27, which is more than 26. Hence, this wouldn't have been a valid decoding, but this time it is. So let's continue further. Now we come to index 2, and this time we have only one choice, which is to decode character 6 as F. And again we have come to the end of the string. Hence, this is also a valid mapping. And then we come to this path where we come to index 3. And note that this is like a repeating subproblem. And again, we have only one digit remaining, which is 6, which we will decode as F. And now we have again come to the end of the string and move to index 3, which is the end of the string. And hence, we will return 1 from this path. So, total number of valid decodings is 3, which will be our answer. Now, the time complexity of this approach is O of 2 to the power of n, where n is the length of the input string, because at each step in recursion, we decide between two possible paths, which are 1 digit or 2 digit decoding, and the depth of the recursion is proportional to n. So the overall time complexity is O of 2 to the power of n, and the space complexity will be O of n, which corresponds to maximum depth of the recursion called stack. Here is a quick code walkthrough of the recursive approach with Java code on left and Python on right. We start the recursive decoding process by calling the recursive function, say dfs, with string s and the starting index 0. Inside this dfs function, we first check if the current index has reached the end of the string. If it has, then we return 1 because it means that we have successfully processed the entire string representing a valid decoding path. However, if the character at the current index is 0, then we will return 0, as the digit 0 cannot be mapped to any valid letter according to the rules. Now that we are done with the base cases, we move on to decode the character at the current index by recursively calling this dfs function and passing on the next index, which is index plus 1, and add the result to the answer. Next, we check if it is possible to decode a 2-digit number starting at the current index. For that, we have to ensure that at least there are 2 characters remaining in the string. That is, current index is less than the penultimate index, which is s.length minus 1. If it is, we extract the 2-digit substring and convert it to number. Now, if this number is within the range 10 and 26, it means it's a valid 2-digit decoding. So, we recursively call a dfs function with the next index, which is current index plus 2, to explore the 2-digit decoding and add the result to the answer. And once we are done with all possible decodings, we will return the accumulated answer. Now let's see how we can make this process more efficient. When decoding a substring, we notice there is a repetitive work. For example, in this recursion tree for this small string 226, we see that digit 6 is decoded twice. And similarly for the larger string, the substrings or the subproblems will be decoded multiple times across different recursive paths. So to optimize this, we can observe that if we are at a certain index in the string, the number of ways to decode the substring from that index to the end will always remain same, regardless of the path taken to reach that index. So this opens up the opportunities for memoization or caching. Using memoization, we store the results of the previously computed subproblems in a cache, which can be a hash map or an array. And whenever a substring starting at a specific index is encountered again, we can simply retrieve the cached result instead of recalculating it. Now the time complexity of this approach reduces to O of n because we now process each index in the string only once, and the space complexity remains O of n, mainly due to the recursion stack depth and the memoization table used to store the intermediate results. Here is an updated code using top-down DP approach with memoization. Here we create a memo table, which is hashmap in Java or dictionary in Python, to store the result for each index. Again we start the DFS process, but this time after the base cases, before performing any calculations, we check if the result for the current index is already present in the memo table. If it does, then we return that result. Otherwise, we compute the result and store it in the memo table for that index and return the answer. And improving further, we can also solve this problem using bottom-up DP approach by solving for smaller subproblems first and gradually building up the solution for the full string. This eliminates any recursion overhead. So similar to the caching mechanism used in the previous approach, we can initialize a DP table where each entry dpi represents a number of ways to decode the substring of length I starting from length 0. So for the given string of length 3, we will create the DP array of size 4 with all values initially equal to 0. First, let's look at the base cases. Now for I equal to 0, that is for an empty string, there is only one way to decode the string, that is by doing nothing. Now let's look at the case for dp1, that is number of ways to decode the string of length 1. For that, we have to just look at index 0 in the string and see if the digit can be decoded. If yes, then dp of 1 will be equal to 1 because there is one way to decode the string. Otherwise, it will be 0. For example, here at index 0, we have digit as 2, which is in a valid range of 1 to 26, and for example, can be mapped to b. So, number of ways to decode this substring of length 1 is 1. Now after filling in the base cases, we will iterate through the DP table from I equal to 2 all the way up till n, where n is the length of the string. For example, here n is equal to 3, and calculate the result for each position in the remaining DP table. Now suppose we are calculating the answer for the ith position in the DP table, working in a bottom-up manner. By this point, the answers for all the indices up to I-1 would already be filled. So let's say the value of dp of I-1 is A and that of dp of I-2 is B. Now, the current digit in the string contributes to the decoding of the substring up to index I by either being decoded individually, that is single digit decoding, or forming a valid 2-digit number together with the previous digit, which is 2-digit decoding. In both the cases, it helps extend the decoding process for the string up to length I. So if the current character has a valid mapping, that is, its value is not equal to 0, it can be decoded on its own. This means we can extend the substring of length I-1 to include the single digit, allowing the complete string of length I to be decoded. Hence, the total number of ways to decode the string of length I, that is dp of I, will also include A. In addition, if the current digit and the previous digit together form a valid number, that is, its value is within the range 10 and 26, then in this case, we will extend the string of length I-2 to include these 2 digits, again allowing the complete string of length I to be decoded. Hence, the total decoding ways for dpi in case of a valid decoding will also include B. For example, in this current string, for length I equal to 2, single digit 2 can be decoded. Hence, we will add dp of I-1, that is 1, to this result. Similarly, the last 2 digits, that is 22, is also a valid decoding. Hence, we will add dp of I-2, that is 1, also to the result, making dp of I equal to 2. Similarly, let's fill in dp of 3, that is number of ways to decode the string of length 3. Now the current character is 6, which is a valid single digit mapping. Hence, we will add dp of 2, that is 2, to dp of 3. Similarly, the 2-digit substring, that is 26, can also be decoded, that is, it is in the range from 10 to 26. Hence, we will add dp1 also to dp3, which is 1. So, total number of ways here will be equal to 3. And now that we are done with the whole string, we will return dp of 3 as our answer. Now, the time complexity of this approach is O of n, because each character in the string is processed only once, and the space complexity will be O of n as well for using the DP table. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's get the length of the string. Let it be n. If the string is empty, that is n is equal to 0, or the string starts with 0, in that case, we will return 0 immediately, because decoding is not possible in these cases. Otherwise, we will create the DP array of size n plus 1 to store the decoding counts, where dpi represents the number of ways to decode the substring of length I. Now let's initialize the base cases. dp0 will be equal to 1 because there is only one way to decode an empty string, that is by doing nothing. Similarly, dp1 is equal to 1 if the first character is not 0, otherwise it will be equal to 0. Now we will start iteration on the string from I equal to 2 all the way up till n, where for each index I, we update dpi based on following checks. If the current character, that is character at I-1th index, is not 0, it can be decoded as a single digit. Hence, we will be adding dp of I-1 to dp of I, because decoding ways up to the previous position can now extend to include the current character. Similarly, if the last 2 characters form a number between 10 and 26, it can be decoded as a valid letter. Hence, we will add dp of I-2 to dp of I, because the decoding ways up to position I-2 can now extend to include the last 2 digits. And once the iteration is complete, we can return dp of n as our answer, which contains number of ways to decode the entire string of length n. Now, if we examine this bottom-up DP approach carefully, we notice that for calculating the value at ith position, that is dpi, depends only on the previous two entries, which are dp of I-1 for single-digit decoding and dp of I-2 for two-digit decoding. This means we don't need to maintain the entire dp table. Instead, we can use two variables, say previous 2 for dp of I-2 and previous 1 for dp of I-1. Initially, dp of 0 or previous 2 will be equal to 1 because there is only one way to decode an empty string, and dp of 1 or previous 1 will be equal to 1 only if first character in the string can map to a single letter, that is, its value is not equal to 0. Here, for example, previous 1 will be equal to 1 because digit 2 is a valid one. And notice that this recurrence is conceptually very similar to Fibonacci sequence, except that here the summation is conditional and depends on whether the current single digit or two-digit substring forms a valid mapping. Now we can iterate through the string from index 2 all the way up till n, calculating the decoding count up to that length. For example, for I equal to 2, that is, for the substring of length 2, we know that this character 2 is valid for single digit decoding. Hence, we can add previous 1 to the current value. Similarly, the two-digit substring 22 at the current index is also a valid decoding because it lies between 10 and 26. Hence, we add previous 2 also to the current. So, the value here becomes 2. Now, we can get rid of this value and update the previous 2 and previous 1. And finally, for I equal to 3, we see that the current digit, which is 6, can be successfully decoded. Hence, we add previous 1 to the current value. Similarly, the two-digit substring, that is 26, is also a valid one because it lies in the range 10 and 26. Hence, we add previous 2 to the current value, which results in 3. And again, move previous 1 and previous 2 forward. And now we are done with all the characters in the string. So finally, we will return the answer for the last index, that is previous 1, as our answer. Now the time complexity of this approach stays O of n, as we process every character of the string exactly once, but the space complexity optimizes to O of 1, as we no longer store the entire DP table, but only the last two results, that is previous 1 and previous 2. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. Now again, we will get the length of the string, let it be n, and check for the edge cases, which are if n is 0 or the first character in the string is 0, we will return 0. And instead of now using the DP array, we will just use two variables, previous 2 and previous 1, corresponding to dp of I-2 and dp of I-1. Initially, previous 2 will be equal to 1 because there is only one way to decode an empty string, and previous 1 will be equal to 1 if the first character in the string can be decoded, that is, it is not equal to 0. Now we will again iterate through the string from index 2 to n, and to calculate dpi, we will store the result in the current variable. Now we will check if the single digit can be decoded, then we will add previous 1 to the current value. Similarly, if the current digit and the previous digit form a valid two-digit substring, that is, this number is between 10 and 26, then we add previous 2 also to the current value. And then, after calculating the current value, we will set previous 2 to previous 1 and previous 1 to current value and process the next digit. And once we are done with all the characters in the string, we will return previous 1 as our answer, which is corresponding to dp of n. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.